Okay, this is a quick recording for some multi-choice questions in Analogue Electronics. Let's have a look at this question. What is this feature? Okay, so you can do two things. You can look at the graph or you can look at the answers first. Now, in answering MCQ questions, you never know what the answer is going to be, and it can often be 0. Let's just have a look at this. We start off at 0, and we've got along this axis VCE, voltage collector emitter. On this axis up here we have the collector current IC. So it's voltage over current, so it's obviously an output impedance. Okay, and I've said output impedance. Key reason, we're looking at the output gradients, and these are tending to being flat. They're not quite flat, but they're not bad. So we can clearly see that the real answer for this one is the output curve. Answer B. The input curve of a BJT, just for reference, if I draw a little diagram up here, the input curve of a BJT would look like that. Okay, this will be the value of VBE, and this will be the value of IB, the base current. So the input curve would look like this. This is the output curve. I'll just make a note on there. The transfer curve is the value of beta, so it's a straight line and then it'll tend off towards some limit function. So IC against IB. So we've got all the three curves there, so you can't get that one wrong. I could have also put up on here, for example, a FET, so the correct answer might have been none if I put the wrong one. But in this case, it's answer B. Let's move on to another question. Now we're getting into a little bit of maths. It's simple, okay? What is the correct value for R1? Well, let's just focus. R1 is here. It's the value of the resistor on the bias of this particular transistor design. So we've got to do a little bit of maths, and this is what we know. The power supply is 10 volts. The collector current is 1 milliamp. The emitter is held at 1 volt, and beta is 100. Use the 10 base currents method. Okay, now here's what I would do. Scratch paper, and let's do a little quick drawing. We need something like this, okay? Here's our transistor. Let's put on here what you know. This is why having a bit of scrap paper is really, really handy. This is your value R1, RE. What do we know? We know this. VE, 1 volt. We know the collector current, IC, is equal to 1 milliamp. Okay? We know VBE, it's an approximation. We're always going to assume 0.7 volts. Therefore, we know the voltage across R1. Okay? So let's write out the Kirchhoff's voltage around this loop. The KVL. Simple. It's VR1 minus VBE minus VE equals 0. Okay? We're given VE. We know the approximation for VBE. We need to expand VR1. Okay? VR1 is equal to IB, base current, times 10, okay, times R1. Okay? The base current is equal to the collector current over beta. We know, just put a little tick, we know beta, we know IC, therefore we know IB. We know 10, we can calculate R1. Okay, it's as simple as that. So R1 should equal 1.7 volts divided by, let's put in some numbers, we want 10 times the base current, okay, and the base current is 1 milliamp over 100. So this is the 10 base currents. Remember the 10 base currents method? 10 IB comes down here. Okay, so that's the rule of thumb. We've got our collector current, therefore we can calculate IB, therefore we can calculate 10 IB. It's as simple as that. Pop some numbers in, we suddenly realise we've got 1.7 volts divided by 0.1 milliamps, which equals 17 kilo ohms. Okay, let's go back to our question. Easy. So some of these questions, when you look at MCQs, you've actually got to know how to do a little bit of rough work to then go back and calculate. Okay, and make no apology for that one. People think multiple choice questions are easy. Not necessarily if you don't know your material. Okay, that's a solution. Question 3. Well, we've already sort of done this question because we've done it in that one. It's a very similar question. In this case, we don't actually have a calculation to make. We don't have a number to do. What we're going to do in this case is we're just going to calculate the Kirchhoff's voltage loop. So let's do that here. Okay. Down here, we've got 10 IB. In here, we've got IB. Here, we know VBE. And here, we're going to have VE. Let's assume this is IC, which is equal to beta IB. Okay, so we know an awful lot about this one. I wonder what the current is here, IE. Well, quite often we would say IE is approximately IC. Sometimes we say we can't do that, so IE is equal to IC plus IB. If you know one of them, you can write it together. So IC is IC over beta. There we go. We can factor that out and put it in terms of beta. So let's have a look at our answers now. 10 IB RB. Okay, so that's this voltage generated here. That's correct. Okay, that's a good term. Minus VBE minus 1 plus beta IB RBE. So what's that current? 1 plus beta IB. That's IC. So that's a good answer, but it's not necessarily the perfect answer because it's not the collector current. And nothing in the question here says we can ignore base currents. So if it had to ignore base currents, that would be a good answer. Let's look at the next answer. 10 IB RBE, yeah, VBE, IB beta. Okay, that value is your collector current. Sorry, this one here, 1 plus beta is IE. Okay, this answer is IC. So you've got what the top one is IE, the emitter current, and this one is IC. So quite often B would be your choice because you make this approximation. If you don't make this approximation, it looks like A is a good choice. Let's have a look at the other two answers. IX RB. Well, we don't know what IX is, therefore we can throw that one away because we're not defined that. Let's have a look at this point D. 10 IC over beta over RB. IC over beta is IB. IB over resistance. Current over resistance is one of the voltages, it's conductance. So this term is wrong. Okay, so this one we can throw away. This one we can throw away. So we're now left with 2. Now we have to make a judgment. Which is the best answer? The question doesn't give away whether we want accuracy or not accuracy. In this case, we want A. Okay, we're selecting the best answer that we can see. It's an interesting puzzle, isn't it? Let's have a look at this question. Okay, what is the output resistance of this transistor? So we're now we know now this is the output curve from this MCQ. So what we need to do is we need to work out what the gradient is. We need to work out, delta IC against delta VCE and calculate a resistance. Let's have a look how we can do that. I'm going to expand this a little bit so that the diagram's a little bit easier to read. Here's our graph, and I've put a nice slope on that. IC, VCE. Now I picked out a couple of values on that graph that look pretty good. 7 volts, 1 volt. 1.9 milliamps, and here 2.1 milliamps. Now that was just particular numbers on this graph. So if I want to now calculate RCE, the output resistance of this device, I want to look at delta VCE over delta IC. So that is equal to, sorry, it wasn't 7 volts, it was 8 volts. Okay, it was an 8 volt scale. So again, 8 minus 1 is the 7 volts, 2.1 minus the 1.9 is 0.2 milliamps. Okay, so now you're looking at the gradient, okay, of that line, and that's the value of the resistance. In this case, 35 kilo ohms. Okay, back to our question. Let's have a look here. Oh, look at that one. I've deliberately put in 3.5 kilo ohms if you dropped a factor. So the correct answer is C. Sometimes you might get none of the above being correct, and I just put my random numbers in. So then you have to really think and think, hang on, I'm sure it's this value. I'm going with it. That's it. And bingo. Now I chose this point and this point on this curve. If I'd chosen this value and if I'd chosen this value, okay, up here, we would have had slightly different values. Okay, as you can see from that, the gradient increases as collector current increases, your gradient increases. So I just chose the one in the middle. Last, or almost last question. There is a bit to this question. What is the correct equation for V in? Okay. Now what you've got to say is, I don't know what the current coming in is, but I do know the current IB, and I've got a resistor here, RBE. So the volt drop across that resistor is IB RBE. Now we have to apply Kirchhoff's current law. We have the base current coming in here, IB. We have beta IB coming down here from the collector. So the current coming out here is the sum of those two. So the current flowing is 1 plus beta IB. Okay, in RE, multiply by RE, that gives me the potential at that node. So just by inspection I can clearly work out what the volt drop is. So let's have a look at these expressions here. IB RBE, that is correct. IB beta RE, that's accounted for the collector current but not the base current. IB RBE, that is correct. 1 plus beta over beta. So if beta was 100, that's 101 over 100. So that's 1.01 times IB. So that's just wrong. Okay, so we can throw that one in the bin. It's just incorrect. Now we have a look at this expression here, IB R1 R2 in parallel. That's the parallel symbol here. We can throw that one away because we don't know what the input current is, IB. Look at the bottom one, IB RBE, IB plus IB beta RE. 1 plus beta IB, if we took the IBs out. So this one's correct. This one's close. Again, you have to make a judgment. Sometimes this will be the correct answer. However, in this case, this one is the correct answer because it didn't tell you to ignore base currents. If it told you to ignore base currents, you could talk about this one, but this is the best answer. Okay, question 6. Question 6 is quite straightforward, okay, but you've got to think. This circuit is working correctly, okay, with a supply voltage and with an output voltage that's half the supply voltage. If we change the transistor, the BJT, so that beta increases, what happens to VC, this output voltage here? You know, the collector voltage at this node. Does it go up with the value of beta, or does it go down with the value of beta? Let's draw a little sketch. I always like my little sketches. Okay, so we've got a constant current source here, bias. Here's our transistor, RC, RB. Okay, VBE, sorry. Right, let's just have a think. VCC. Value here, VC, the absolute voltage at the collector. Let's just write out an expression, shall we? What's the value of VC?